Welcome back. So this is part 3 of section 4.1. After all this abstract nonsense, let's actually prove a particular semi-classical limit. And let's do this for probably the most important case, Gaussian wave packets. For simplicity, let me just focus my attention, at least initially, on dimension 1. And then say a few words on how to extend it to higher dimension. So what we should start with is the type of states that we're interested in. And the Gaussian wave packets, let's assume that they're of the following form. So I will call them phi epsilon. And they depend on a whole bunch of parameters. So they depend on an average position Q, an average momentum P. Then I have two parameters alpha and beta. I have a phase nu and a normalization n. And of course, they should be regarded as a function of x. So first off, I have a normalization factor. So later on, I will just choose this normalization factor so that this guy here is normalized to 1. Then there is a phase factor that will later on become a dynamical phase. So this is to accommodate dynamical phases. Then there is a shift in momentum space. This is just p dot x minus q. And then I have the Gaussian factor. So this is I divided by epsilon alpha plus I beta times x minus q squared. So let's just have a closer look. So the normalization prefactor is clear, I think. So this here, this factor is necessary to accommodate the dynamical phase. This here is a shift in momentum space. By p. So this prefactor here ensures that the Gaussian wave packet has average momentum p. And then I have the Gaussian itself. And of course, if you have very good eyesight, you see that, okay, there's an I beta here, there's an I here, which gives me a minus beta. So this is only a Gaussian in the sense that it's super exponentially decaying if beta is positive. Okay, and this means we have already found our constraint manifold. So the approximation manifold M consists of such Gaussians. evidently, this is square integrable in x. So these are elements of L2 over R. We are in one dimension. And okay, the Q, the parameters Q, P, alpha, and nu are real valued. And beta is positive. And the n is such that the L2 norm of phi epsilon is equal to 1. So I think this is very intuitively clear. So momentum and position, they can be anywhere. Then there can be a complex prefactor that is quadratic. There is a dynamical phase. Then there's a parameter that characterizes the width of the wave packet. And I just normalize the wave packets to 1. Okay, so I think this is relatively clear. But there's one thing that is implied here, and I think that should be made explicit. So these wave packets, they have a width, so a width in real space. And this width, if you look closely, so you can see this best here. So the width of a Gaussian is the square root of this prefactor in a sense, right? So the width here is square root of epsilon, and this is because here we're using macroscopic units. So this is in macroscopic units. Spatial units. So here I'm choosing to go from microscopic to macroscopic spatial units, where the Schrödinger operator has the epsilon squared prefactor in front of the Laplacian. So I'm also reintroducing the factor 1/2. And there's no epsilon prefactor in the potential. So this is just the Laplacian in macroscopic spatial units. And okay, why is this important? Well, if we're using macroscopic units, the microscopic length is epsilon, and the macroscopic length is order 1. So this, the width of the wave packet is large on the microscopic scale, but it's small on the macroscopic scale. So let me just write this as a, let's say, as a stupid inequality. So epsilon is less than square root epsilon, and that's less than 1. Right? So what this here should tell you, so this is the microscopic lengths. They are small compared to the width of the wave packet. And the width of the wave packet is small on the macroscopic scale. And if you think about this, that's a very nice property, because now on the one hand, if you take the limit, let's say just conceptually, the limit epsilon goes to 0, then on the macroscopic scale, the wave packet looks like it shrinks down to something like a delta function. But microscopically, you can still use slow variation, right? Because on the microscopic scale, the difference between the width of the wave packet and the microscopic scale is a factor of square root of epsilon. And this is precisely what is used in the proof. So before I give you the proof, let me make a comment that will immediately explain what we are doing in the proof. So, and that is connected to the question, why are Gaussians, or why do Gaussians have a nice semiclassical limit? And the answer is very simple. The answer is Gaussians are exact solutions to the Schrödinger equation when the potential is at most quadratic. So when v is a degree less than or equal to polynomial. And now all we need to do is if we're confronted with a generic potential that is regular enough. Remember, I always emphasized that in order to have a good semiclassical limit, you have to make some regularity assumptions on the potential. And here, the regularity assumptions are very, very simple. Namely, you need to be able to Taylor expand the potential. Let's say I Taylor expanded around Q. So let me already introduce the terminology and notation that I will use in the proof. So I get the constant term, the linear term, and now the quadratic term. And now I'm getting terms of higher order, but let me already give this guy a name. So let's call the remainder WQ of x, where of course WQ of x is third order. And that's already the idea, right? So pictorially speaking, let me explain how things work here. Because the width of the Gaussian is square root epsilon, it still varies slowly on the microscopic scale. So for each position Q of t, you do the Taylor expansion around Q of t. And because the width of the wave packet is small on the macroscopic scale, the potential does not appreciably vary over the width of the wave packet, at least if you choose epsilon small enough. And so this remainder term is expected to be small, right? Because Gaussians have super exponential decay. So now it's also clear that what we have to do if we want to actually prove it, we have to make some assumptions that ensure us, that allow us to control the remainder term rigorously. And that's indeed exactly what happens. So the one condition on the potential is that there exists a Taylor expansion up to second order. And then we need to control the remainder. And these are exactly the conditions that are appearing in the theorem. So let me write the theorem on the next page. So suppose the potential satisfies well, condition A, well, it's 3 times continuously differentiable, so that it has a Taylor expansion for sure. And in order so we also need to control the remainder. So let's assume, in addition, that the third order derivative is a bounded function on R. And that's that. Then for any starting point on our constraint manifold of Gaussians, so remember, this means we have a bunch of coordinates. We have Q naught, P naught, we have alpha naught, beta naught, nu naught, and n naught. So these are just the coordinates of phi naught in our manifold. But I'm emphasizing this because we will need the initial conditions later on. Then for any initial condition and t greater than 0, so this is the maximal time for which this holds, there exists a constant so that if we look at the norm difference between the true solution to the Schrödinger equation, which is psi epsilon, and the element of best approximation, that this is less than or equal to set constant c times t, and importantly, times square root of epsilon. So the error scales like the square root of epsilon. So psi epsilon solves the Schrödinger equation, and phi epsilon is the element of best approximation. Whose first two components satisfy the classical equations of motion. So of course, implied here is that the initial position is q naught and the initial momentum is p naught. So here I've chosen the mass to be 1, so q dot is equal to p, and p dot of t is minus the gradient of v evaluated at q of t. So just as a comment, the other parameters can also be deduced. They're also dynamic, but in some sense they're only slaved to the position and to the momentum of the particle. And you can see this already from the Taylor expansion. So the roughly speaking, the second order derivative tells you the width of the Gaussian, so that you have an exact solution. And this is, for example, how the position, because the second derivative is evaluated at the mean position of the Gaussian, this is how the mean position determines the width of the Gaussian beta. So of course I'm not writing out all of the details, but I think this is the level of detail that should be good enough for you to follow along in what sense you have a semiclassical limit. There's one technical statement that we will need in the proof. And that is to actually, this is actually the crucial technical estimate to make everything work. So this is a so-called a posteriori bound. So this is an a posteriori error bound. So why is it called a posteriori? Well, we have to assume that we are already given an element of approximate solution. So suppose we are given an approximate solution . So of course, I mean by what I mean by this is an element of best approximation with respect to the approximation manifold to the exact solution. Then we can bound their distance by well, we just have to integrate up the distances of the instantaneous time derivative, which is 1 over I epsilon times h epsilon applied to our approximate solution, to the tangent space at the point phi epsilon of s. So I will not give a proof, but you can already tell from the geometric picture why this is likely, or why it's reasonable that this this is a good approximation. So let's just fix a point in time. Then 1 over I epsilon times h epsilon applied to phi, that's this vector here. And this is the in-plane projection. So the distance between the two is this here, the length of this difference vector here. So at most, the distance between the two is, okay, I just have to integrate up all the distances here. Because remember, this is the minimizing distance, so I just have to integrate it up over time. And that's exactly what I get here. But a rigorous proof, while not difficult, I'd rather use the time finishing the proof of the original statement. So this here tells the first thing that we will do is we can estimate the distance of I divided by 1 over I epsilon times h epsilon applied to phi epsilon of s to the tangent space at phi epsilon of s. Well, we can estimate this by simply the norm of 1 over I epsilon h epsilon phi epsilon of s. Right? Because the norm is maximized in case this vector here is orthogonal to the tangent space. Right? Otherwise, it is smaller. And this is this approximation here. And okay, let me just rewrite this. So there's a factor 1 over epsilon, and then I just have to estimate h epsilon applied to phi epsilon of s. But now, what you have to keep in mind is that phi epsilon solves the Schrödinger equation exactly in case I'm dealing with a Gaussian, a quadratic potential. So Gaussians are exact solutions to quadratic potentials. And that means that and I'm using the notation introduced on the previous page. let me write this down in an intelligible way, to H epsilon, where the potential is a degree less than or equal to polynomial. So that just suggests to use the splitting I introduced before. So I have a quadratic term. So this when the second derivative is non-zero, this is just a fancy way of writing down a shifted harmonic oscillator. So here Q of t is the Q coordinate for, sorry, not of t, of s, is the Q coordinate of phi epsilon of s. Remember, by assumption, this solution lies in the constraint manifold, so I can use position, momentum, and so forth as coordinates. So here I'm expanding around the mean position. And then the term, so let me close this. And then there's a second term, which, if you remember, the remainder of the Taylor expansion, I just dubbed WQ, in this case Q of S. Applied to phi epsilon of S. And now, because Gaussians are the ground state wave functions to the harmonic oscillator, once I choose the right parameters to offset this guy here, what I can do is I can make this here vanish. So this is this here used in here, and all that remains is the remainder of the Taylor expansion of the potential applied to phi epsilon of S. So that's very, very simple. And now the next, you can already see where this is going. Now we use the bound, the fact that the third order derivative of the potential was bounded by assumption. That means that the potential WQ of S can be estimated in absolute value by some constant C prime times x minus q of S cubed. Right? This is just saying that the remainder is big O of x minus q of S cubed. And because this the third order derivative is assumed to be bounded, I can choose this constant C so that this holds everywhere in X. And okay, this is enough, because if you remember the crude estimate of the integrand in our a posteriori estimate? Well, just reduces to the norm of this here. I can plug in this estimate for the potential, for the remainder of the potential. And what I'm left with is so the first one is even inequality. Then I'm using this estimate here. So this is less than or equal to the norm of x minus q of s cubed times phi epsilon of s. So now this is a Gaussian. So this integral can be analyzed very explicitly. And one thing that becomes clear, because the width of the Gaussian is square root of epsilon, that means that this factor here is epsilon to the 3/2, right? Because you have a power 3 here. So this scale, and the width is square root of epsilon, so I have to take the third power of square root of epsilon. So this is less than or equal to some other constant c prime, 2 prime, double prime, times epsilon to the 3/2. And if you remember, this distance came with a prefactor of epsilon inverse. So all we have to do now is we have to multiply with epsilon inverse, which gives us, so maybe, so 3/2 minus 1 is square root of epsilon. And then we need to integrate this up from 0 to capital T. And this gives the proportionality, that the error is proportional to T. And this finishes the proof. So let's go quickly through it again. So I made a very crude estimate for this distance that entered the a posteriori bound. So I just have the epsilon to the -1 times the norm of h epsilon phi epsilon of s. Then I'm using a suitable Taylor expansion of my polynomial, using the fact that Gaussians are exact solutions to potentials of degree less than or equal to 2. So which means that only the remainder matters. Our assumption, boundedness assumption on the third derivative of the potential, then translated to a bound on the remainder of the Taylor expansion, which then gave us the right behavior in epsilon. And then integrating everything up means that in addition we get a term that is proportional to the time t. And that's that. So let me maybe finish with an extension to a dimension greater than 1. Let me finish by explaining how to make the extension to higher dimension. So in principle, the theorem that I just proved, I mean, you can just inspect the steps and you could correctly guess that an extension to higher dimension is straightforward. Indeed, what I did was I took the proof for the general case for d greater or equal to 1, and I simplified it for d equal to 1. So the above theorem extends to higher dimension. And let me just give you a flavor of the types of equations that appear. And to do that, I need to introduce a way to generalize Gaussian wave packets. And one very neat way to do this is due to Hagedorn, George Hagedorn. This is a work from 1998. And in addition to, so he chose a different parametrization. In addition to Q and P, which are your phase space variables. So this is from RD cross RD. Or if you want to be conceptual about it, the cotangent bundle of RD. And in addition, he has two d by d matrices, which are real symmetric. And with complex entries. And these matrices satisfy certain relations. So they're not independent. So you can think of them as consistency relations. They are preserved under the dynamics. This is something you can prove. And then you can parameterize your Gaussian wave packets in terms of Q, P, capital Q, capital P. So small q, small p are elements of Rd. Capital Q and capital P are matrices, are real symmetric matrices. And you could ask yourself, well, okay, why are they called Q and P? You will see in a second once I write down the classical equations of motion. Then it will become extremely obvious. So Hagedorn chooses his wave packets so that they are already normalized correctly. So you have a prefactor pi times epsilon to the power minus d over 4. Then you take the determinant of q and raise it to the power minus 1/2. So one of the conditions, one of the consistency conditions, or something that is implied from the consistency conditions mentioned here, is that q is invertible. So this prefactor is nicely behaved. Then you have the shift in momentum. So this is as before. The only difference is, of course, that you have to introduce a dot product. And then you have the Gaussian factor, which is now written as I divided by 2 epsilon. And now you take the dot product of x minus q with p q inverse applied to x minus q. So just a quick consistency check. So this is if you believe that the matrix Q is invertible, this is the product of two D by D matrices. It's a D by D matrix. So this is a D by D matrix applied to a D vector, which gives me a D vector. So this is a good argument for the dot product. And so this is just the dot product of two vectors in RD. And the imaginary part of P times Q inverse this imaginary part defines the shape of the Gaussian. So this particular parametrization at first glance does not seem to be very nice, and you could propose an alternative one, but the advantage of that will become clear once you write down the equations of motion. So first let me say that the purpose, and this is clear from the equations, of P and Q is to adapt the shape of the Gaussian to fit the shape of the potential to second order. So this is just the Hessian of the potential at the point at the center of the wave packet. The Hessian, in case you're not familiar with this terminology, that's just a collection of second order derivatives arranged into a matrix. And okay, let me now reveal why P and capital Q are named as such, and why it is convenient to factor the two matrices that determine the shape ultimately in this particular fashion. So the classical equations, so first for the small variables, they're just your usual equations. And let me now, for simplicity, to be able to compare the equations for small q and capital Q, let me now arrange them in this particular fashion. So Q dot is equal to P, since we've set the mass equal to 1. Then the equation for capital Q dot, that is P, capital P, nice. Then the equation for small p, well, it's minus the gradient of V. And the equation for capital P, well, it's minus the Hessian of V. And it's perhaps worthwhile to add the time dependence more explicitly. So of course, the gradient and the Hessian are evaluated at the position at the center of the Gaussian wave packet. And that means, if you look at it, that the equations for capital Q and capital P are dragged along the equations for small q and small p. So they're, in some sense, slaves to the translational dynamics. So the small q and small p dynamics are independent of capital Q and capital P, so there is no back reaction, and the dynamics of capital Q and capital P they depend on small q of t only, and there's no back reaction. Back reaction just means that the dynamics of capital Q and capital P does not influence the dynamics of small q and small p. And in this sense, if you want to have a semi-classical picture, you can sort of forget about those and think of capital Q and capital P as instantaneously adjusting to the potential at position Q of t. And of course you have momentum P of t that determines where the wave packet is going next. So in this sense, these are the decisive semi-classical equations. All right, with that, we're done in this part. Next, we will explore how this has been adapted to condensed matter physics.